Hey, Math 2403. Here we are, Unit 2, video number 1. Today we're going to start talking about probability. We'll do so basically from an approach of the way probability originated. The study of probability sort of happened by people studying games of chance. Basically, gambling sort of drove the fundamental principles of probability. Ultimately, we will apply probability to some applied situations that will work for us, such as we'll discuss reliability, which is a really nice application of probability. We'll talk about expected value, which is another application that will be applicable in your field. And this will also get applied when we start doing decision making or that topic of inferential statistics. So probability, we need to get a basic understanding of it so that we can do some of these more specific applications that are more applicable. But at the beginning, we start out with things like, picking cards and drawing dice, hopefully things that we're familiar with. So let's get to it. In Unit 2 here, we're going to talk about probability. Probability will be given sort of as a function notation. We'll use the letter P for probability, and then we'll have it be like, instead of f of x, we'll have P of A, the probability of some event A occurring. So that's our general notation for probability. We have two main approaches for doing the calculations. Why don't I talk about the second one here first? The classical approach is where you count up all the number of ways that something can occur, and you divide that by all the possible things that could ever happen. We can denote it with S over N. Now this is the ideal because we can get the exact value. But there are many situations where we can't necessarily accomplish the counting. It's hard to count the number of ways some event can occur, and it's also hard to count the number of possible outcomes there might be. So sometimes we have to take an experimental approach to this, and that's what this relative frequency approach to probability is, where you basically repeat an experiment over and over and over again, keeping track of the outcomes and the number of times that some sort of subset occurred, some event A. So you count how many times A happens and you divide it by the number of times that you did the experiment. You'll see here that in the notation we don't get the exact probability using this, we just get an estimate. But oftentimes this is the best we can do. What are your chances of, getting some sort of disease? We can't necessarily, count all the different ways that you could get it or all the, all the possibilities. So we would have to look at experimental data. So we do use both approaches here quite a bit. The nice thing about them is that this experimental version will actually get very close to the classical or theoretical answer as long as you repeat your experiment enough times. And that's this law of large numbers. The more times you repeat an experiment, the closer your relative frequency probability estimate will get to the actual probability. So here's a little graph here of flipping a coin. Suppose I'm interested in how many, the probability of getting heads. So I flip a coin one time and I got a heads. So I would at that point estimate that my chances of getting heads are 100%. I flipped it one time and I was successful that one time. But as I continue flipping the coin, by the time I have flipped the coin, say 30 times, you can see that we're getting pretty close to the actual probability of getting heads, which we know is 0.5, because we could calculate that using the classical version. There's a coin that has two sides, so there are two possibilities. One of them is heads, so the probability classically is 1/2, and you can see from my experiment that that's what this is trending towards. So after 100 flips, I'm a little overestimating looking at this graph, but if I continued to flip the coin 1,000 times or 100,000 times, this thing would be zeroing in on the 0.5. So the law of large numbers is powerful that way. I tested the law of large numbers by I took a single die and I rolled it a whole bunch of times. I was interested in what's the probability of rolling a 3. So probability of rolling a 3 on a single die. Now we know the classical answer to this. A single die has 6 sides, only one side has a 3, so we know the answer is 1 in 6. But I was mostly trying to annoy my wife, so I did the experiment of rolling this die on a glass coffee table while we were watching TV one night. So after 10 rolls, I had seen 2 3s. And you can just imagine how noisy it is when you roll a single die on a glass coffee table. 2 out of my 10 rolls ended up being 3s. Turned out to be 20% at that point. I kept going. When I hit 100 rolls, I had seen 14 3s. So now my probability is 0.14. At 1,000 rolls, I had hit seen 162 3s. Now, that estimate is getting pretty close to the actual value. You can see I was at roughly 16% of my rolls, which if you calculate 1/6, you'll see that these two numbers were pretty close, to 2 decimal places I was matching. So if I had continued to roll it a little bit longer, I probably would have been divorced, but I probably could continue to get closer and closer to 0.167. So that's just trying to show you the power of repeating an experiment a large number of times in order to estimate a probability. A question that's a little more difficult than rolling a die might be dealing cards. Now in this course, I won't assume that you know how to play poker or know how to play any particular game. I will describe games if I ask you a game question. Try not to give people that play certain games a big advantage. I will assume that everyone knows what a deck of cards is. So make sure you know a deck of cards has 52 cards in it. Half are red, half are black. You need to know that the suits are, diamonds, club, hearts, and spades. I know a lot of people don't play a lot of cards, but I'll make those assumptions that you know the makeup of a deck of cards. Here's a little example then using cards where we're playing poker, and in poker you make a hand out of 5 cards. 5-card stud poker is special in that you never get to do anything weird. You don't draw any additional cards ever. You don't get to play with community cards on the board, as they say. For those of you who play, games like Texas Hold'em. I'm curious in finding the probability of getting a flush And a flush means that all of your cards are the same suit. So all diamonds, or all hearts, or all clubs, or all spades. Here's an example of one that's made out of 5 clubs. So if I just deal myself 5 cards out of a deck, what are the chances that they'll all be clubs or hearts or diamonds? And it's a hard thing to calculate directly, maybe, because it's hard to count all the different ways that this can happen. Even if I just focused on clubs, how many different flushes are there from clubs? And in this sort of thing, you have to worry about, does the order matter? And the answer is no. If I have the cards 3 of clubs, 4 of clubs, jack of clubs, 8 of clubs, ace of clubs, I could mix them around any way I want, and it's still the same flush. So the order doesn't matter, but I still have to keep track of all the different ways I could make it up. Sure, I could have instead used 5 different cards. 5, 6, 7, queen, king is another possible flush. So counting all the possible flushes here, if we tried to, make a list, I think we'd be here a long time trying to list out all the possible ways we could do it. And that's based on just, say, clubs. We'd have, an equally large list for hearts, and then an equally large list for diamonds, and then an equally large list for our spades. So what I did, I teach computer science students, so I wrote myself a little computer program to basically do an experiment. At first, I tried just dealing out the cards. I got a deck of cards. I dealt out 5 cards. I looked at them and I went, is this a flush or not? And then I shuffled the deck and then I dealt out 5 cards and I asked myself, is this a flush or not? The problem with this approach is that it takes a really long time. Rolling the die was pretty quick, but dealing out 5 cards over and over and over again was tedious. So I relied on random number generator to help me out. What I would do is I would generate 5 random cards. And if they were all the same suit, I would say, yay, I have a flush. If they weren't all the same suit, well, then I wouldn't count that one. And I would keep track of how many times I dealt out 5 random cards. I had to be a little bit careful. I realized after I wrote the program that in poker, there are special flushes. Like there's a straight flush and a royal flush. And those are flushes that are in order. So I wanted to rule those out. I would put those in a different category. So I basically kept track of those separately. Like if you get a straight flush means you have them all in order. So say you had 3, 4, 5, 6, and 7, and they're all hearts. That's a straight flush. And that's a special type of hand in poker. So I didn't want to count when that happened. I didn't want to just call it a flush. So I fixed my computer code, and then I had it repeat this over and over again a lot of times. I won't bore you with the computer code, but here's kind of the crude output. Here's my program name was Flush, and I asked it to deal a whole bunch of hands. 100 million. So I said, hey program, deal me 100 million hands of poker, and then check each one to see if it's a flush or not. And the results then, after it took 100 million is a lot of random numbers to generate. It took a few minutes to run, but after a few minutes, I got some results. And I got 998 million times I didn't get a flush. But 197,000 times I did. And I kept track of the straight flushes and royal flushes just for fun. To calculate my probability of a flush, then I took my 197,000 successes and I divided it by my 100 million. And I got this as an answer. I know the exact answer, the exact theoretical probability of getting a flush, and I output that as well so we could compare them. You can see that to roughly, what is it, at least 4 decimal places, we match. So it took me 100 million tries to get 4 or 5 decimal places of precision. I checked the straight flush and royal flushes just to see how well I was doing there, and I was even doing a little bit better in my precision. I was ending up at, the 6th decimal place or something. You can see I was I estimated a little bit low on the straight flushes, 137 versus 138 here, but I was a little lucky on my royal flushes. I dealt out more royal flushes than what I normally would expect. So I calculated the errors here. These are just the differences of these values, just to see, how far off we were. So that's one way to do it. You can take advantage of these random numbers to help you estimate probability. The actual number of flushes is 5,108, and there are 2.6 million different poker hands. So that's how you calculate the probability using the theoretical version. But it's difficult to get these numbers without spending time learning permutations and combinations. So speaking of that counting, you'd think that counting would be an easy thing. I mean, you learned how to count, and before you could even get to school. But counting the number of outcomes of things is a difficult process. I thought we'd study, you know, a lottery that we all might be familiar with, the lottery 649. I think it has a couple drawings a week. The way it works is there are 49 numbers. And if you want to buy a ticket, you are choosing 6 numbers. And you hope that your 6 that you picked match the 6 that are actually drawn. So we'd like to calculate then, what are the chances of winning this thing? Like, should we ever play the lottery 649? We have this fundamental counting rule where basically you just multiply the number of ways things can happen times each other to get a total. So I listed it out here. I have event A1 and it has N1 ways of happening. Event A2 has N2 ways of happening. So if I want to find the total number of things that I can have, I just multiply all these n's together. With the 649, the first number that I draw, there are 49 different options. But after I make that draw, the number doesn't go back in and isn't allowed to be picked a second time. In 649, the drawing is unique. You can't draw the number 111111 because once you draw a 1, it can't be picked again. And that's how we describe then the next value we pick. There are only 48 choices left on our next pick. And then there are 47 choices and then there are 46, and then 45, 44. So to make 6 picks, we'd have 49 times 48, 47, 46, 45, 44. And if we multiply those numbers together, yikes, we get a big number, 10 billion. There are 10 billion different ways to draw 6 numbers out of a group of 49 numbers. But that seems kind of big. I think we're on the right track to figuring out how many different ways there are to draw 6 numbers out of 49. But I don't think this is our answer, because I don't think anyone would ever win the lottery if there were 10 billion choices. Think about Canada. If we only have 30 million people and maybe a third play the lottery, I think that might even be high. That means that we'd only be selling like 10 million tickets at a time. The chances that somebody wins is pretty low. And it seems like somebody does win this thing pretty frequently. So I think we're maybe missing something. I started to try to draw it out just to get a feel for the thing. Suppose I drew a 1 for my first number, and then I drew a 4 for my second number. And then I drew, say, a 6 for my next number. Well, maybe I should draw a 2 for my next number. Suppose I drew a 2 for my first number. I might draw a 4 for my second number, and then maybe draw a 1 for my next number. You'll see that in the first list here, I had 1, 4, 2, and then 3 more numbers. Or I could have gone 2, 4, 1, and then my remaining numbers. You'll see that it's possible that I could repeat the same outcome, just in a different order. And you don't have to pick the order that the numbers are drawn in. Like if the numbers are drawn 1, 4, 2, 1, 4, 2, 16, 22, 48, you don't have to pick them in that order. You could have picked 48, 22, 16, 2, 4, 1. So the order that you pick these doesn't matter. But this 10 billion does assume that the order does matter. So that's why this number is so big. It shouldn't necessarily be that big for the lotto draw, because we're repeatedly counting the same thing. These two lists are the same. So how do we fix this? I did an example with, just trying to keep it simple, 1, 2, 3, 4, 5, 6. How many different ways can you rearrange that one outcome? Well, you have 6 choices for your first pick, then 5, then 4, then 3, then 2, then 1. If we multiply all those together, you get 720 ways. So this group of 1, 2, 3, 4, 5, 6 can happen 720 different ways. So each group of 6 got counted 720 times. So to fix that, we can just divide our 10 billion by 720. Because each outcome in this 10 billion was counted, had a multiple twins. Every possible 1, 2, 3, 4, 5, 6 appears 720 times in that 10 billion. And so does 2, 3, 4, 5, 6, 7. And so does 8, 9, 10, 11, 12, 13, etc. So if I just divide by 720, now I get the number of combinations. There are roughly 14 million different lottery tickets in the 649. So your chances, they only draw one correct answer. So your chances of winning this thing are 1 out of roughly 14 million. So the question is, should you ever buy a ticket? Well, 14 million is a big number to try to swallow. To put it in perspective, there are roughly 300 people in the United States that are killed by lightning every year. And they have roughly 300 million people, just to keep the numbers, reasonable. So your chances of getting killed by lightning in the United States are roughly 300 divided by 300 million, or 1 in a million. So you have a 1 in a million chance of being killed by lightning as an American. But you only have a 1 in 14 million chance of winning the lottery. So I hope that puts it in perspective. You have a better chance of getting killed by lightning 14 times than you do by winning the 649. So, and I mean, this is a biased, this is an example of biased statistics here, because not everyone in the United States is equally likely to get hit by lightning. Certainly, certain regions of the country are, more prone to lightning, etc. Or certain regions are maybe more prone to people sticking their golf club up in the air during a lightning storm. But just to get an overview of what 1 in 14 million chance. So I know people who do play the lottery, and they use the argument, well, somebody's gonna win, and that is true. The draws keep going until somebody wins, and you can't win if you don't have a ticket. But some people go out and buy 100 tickets, thinking that's really going to help them win the jackpot. Well, 1 out of 14 million or 100 out of 14 million, you still really have no chance. So if you ever are going to buy a ticket, buy one. It lets you buy the chance to dream. I think that's what you're really doing when you buy a lottery ticket, is giving yourself the ability to go, oh, well, if I won this, I wouldn't have to write my midterms. I could just retire now. So yeah, that I can put this another way to help. Besides the lightning example, I looked up some highway statistics. I was curious as to I wanted to answer the question of, am I more likely to die buying my ticket than I am of winning? So I looked up some highway statistics, and I found that uh, there's approximately 1.7 deaths for every 100 million miles that people drive in their car. Uh, I clocked it, the distance from my house to 7-Eleven was 3 miles. Yeah, I'm American, so I went with miles. Uh, so a round trip for me to get a lottery ticket is 6 miles. So I take my 6-mile travel distance and I multiply it by that rate of death, 1.7 fatalities per 100 million miles driven. And that gives me this probability, which is a fairly low-looking number. But when you convert this decimal into a fraction, it's 1 in 9, almost 10 million trips. So if I go to buy lottery tickets 10 million times, I expect to die one time. but I need to buy 14 million tickets before I start to think that I'm going to win. So I actually have a slightly higher chance of dying in the process of getting my ticket than I do in winning on the ticket that I bought, which is, kind of amusing. It's again a biased statistic. Uh, I couldn't find, uh, very specific statistics for driving around on more residential type streets. Like these are highway statistics, and your chances of dying on the highway are much higher because you're going at higher speeds. So I'm guessing my chances of dying might be a little bit lower actually than my chances of winning a lottery ticket because I don't need to travel on a highway to get to the nearest lottery retailer. Uh, but if I did, then this would be pretty accurate. I think this is a good little introduction to probability. It's a little fun. Next time we'll dive into the basic rules of probability, and we will then do a whole bunch of examples. So hope I will see you there. Take care for now.